Here we go with Chapter 3, Section 2. We're going to talk about the structure of the atom and some of the past experiments that have been done early on to give us a little idea of what exactly is in an atom. So starting off, the atom, here's a few definitions. It is the smallest particle of an element that retains the chemical properties of that element. If we go back and we just mention again Dalton's atomic theory, he thought that atoms could not be broken down any smaller, but we are going to look at why that is no longer the case. The nucleus is going to be a part we're going to talk about today. It's a very small region located in the center of an atom. So very small within the center of the atom, but it carries a lot of mass. And then we're going to talk about the protons and neutrons that live within the nucleus, how they were discovered, and what their properties are. So again, get you a few definitions there. Surrounding the nucleus are our electrons that are negatively charged, so another subatomic particle. And there's your definition, or the different parts we're going to look at as subatomic particles, sub meaning under or within. So within the atom, we will look at protons, neutrons, and electrons. So if we look at the atom here, on the outside of the atom, we have on the outer rings and rings is used hypothetical, we have our electrons. They are negatively charged. They are located in the electron cloud. So you will hear us throughout this chapter and the next talk about the electron cloud, because we have a lot of models to get to. Dalton was the first model. The size of the electron cloud will determine the size of the atom. So the more electrons it has, in general, the larger the atom is going to be. Within the nucleus, and you can tell here some important information. It is a small, dense, positively charged center of the atom. So it is very small compared to the overall size, but it's very dense, meaning a lot of our mass is packed into that small area. And the overall charge of the center of the atom is positive because that's where your protons and your neutrons live. So please write this information down. I'm going to highlight for you what you need to know. For the electron, the common symbol for it is that E-, and we are going to concentrate on these two parts right here, the relative electric charge and the mass number. So let's go ahead and just look at the word relative. If you were to think of the word relative as far as your family goes, that means you are related to someone else. The word relative here is meaning how is the electron related to the proton, related to the neutron in general, without giving actual specific values. So the electron is said to have a -1 charge as compared to the proton and neutron. So you can tell the charges of the electron and proton are opposite, positive and negative, but the same overall strength of the charge. So a -1 for the electron, a +1 for the proton, and the neutron is going to be given a relative charge of 0 compared to the other two, meaning it is neutral or has no charge. And then that mass number, I do see a relative mass value over here in AMU. AMU is the mass used for individual atoms. If you were to hold just one atom in your hand, you are not going to know that you're holding anything because it is so small. But if you were to look at the actual mass in kilograms, look at these values. 10 to the -31st, 10 to the -27th, that is extremely small masses in kilograms. Kilograms is a unit you're used to. AMU, that's a brand new one on you, but it gets you looking at some numbers that at least we can deal with easily. So for the electron, if I look at the relative mass, 0.000548, that easily rounds to 0. The relative mass of the proton, 1.007, and the neutron, 1.008. Those are both going to round to 1. So that's why you see Sorry about that again. As you can see, if you round off those numbers, the proton and neutron relative to each other to a nice rounded mass number, the mass number is a rounded off number of 1. And then for the electron, we're going to say, okay, based on those other two values, even though there is a tiny mass of an electron compared to the proton and neutron, in the grand scheme of things, its mass is going to be insignificant when we're doing some of our calculations. So we're going to give it a value of 0 even though it's not actually 0. So again, mass number, make sure you get those down for the electron, proton, and neutron, the 0, 1, 1. We will do calculations with those in section 3. And then their relative charge, the -1, the +1, the 0, you will need to know those. So we are jumping right into some videos that go with this section because we're going to get into, okay, what type of experiments were actually run to get to the discovery of some of these subatomic particles. And we're going to start with Thomson's cathode ray tube experiment. You do need to get this drawn into your notes. You need to take great notes over everything that's within the video itself. I will highlight some things for you. Some things are highlighted off to the side of this particular screen. So again, Thomson, his J.J. Thomson, this is the late 1800s. He's going to be given credit with the discovery of the electron. That is big, big news here, the discovery of the electron. And then it gives you his conclusion that he does with this cathode ray tube experiment. This is going to go through. You've got this. Get it drawn before you start on with the audio part of this video.
When the cathode and anode of a cathode ray tube are connected to a voltage source, electric current flows through the tube and can be seen as a cathode ray. The cathode ray is made up of electrons. When a positive electric field is placed next to the tube, the path of the electrons moves toward the field. Using the strength of the electric field and the amount of deflection, J.J. Thomson was able to calculate the ratio of the charge of electrons to the mass of electrons. Imagine a baseball player throwing a ball. Like the cathode ray, with no outside influences, the ball goes straight when the baseball player throws it. A strong wind, however, could blow the ball and make it go off course. An outside positive field attracts the electrons in the cathode tube and makes them go off course. If the baseball player threw a lightweight plastic ball instead of a regular baseball, the wind's effect would be even more evident. The mass of the ball is one of the factors that determines the path the ball will take. Similarly, if the wind were stronger and the baseball player used the original ball, the wind's effect would be more evident. The strength of the outside force is one of the factors that determines the path the ball will take. By observing the path of electrons in the cathode tube, Thomson was able to calculate the ratio of charge to mass of an electron.
Okay, so looking at this, make sure you get all the information off to the left side of your screen, talking about the time frame discovery, conclusions for J.J. Thomson's cathode ray tube experiment. And I want to go back and just highlight a few things that they said. In this first part, you got your cathode ray tube set up. Notice that those metal discs on each end, one is positive charge, one's negative charge. So just a refresher for yourself. Like charges, if you put two like charges together, they will repel. Two opposite charges together will attract each other. So in this case right here, when they put a magnet up from the bottom, that's the magnet right here that has this positive charge. Notice when they put the magnet up, the ray, which normally would have just come out, that's that yellow beam of what looks like light, is going from the cathode to the anode. It deflects, it actually attracts the ray towards it, meaning if it is attracting the ray, then the ray must be made up of something of opposite charge. So there's the first conclusion, is whatever is in there is negatively charged particles that make up that cathode ray tube. So that is the first conclusion. It also states within the conclusions that they could look at the ratio of the charge of the particles to their mass, and that is the same. So what is going on with mass? Let me throw in another hypothetical for you on, it's not really a hypothetical, but another part of this experiment. I'm going to use the drawing that is already there, but I want you to envision a paddle wheel that is set up right here. That paddle wheel looks like this. Think of the paddle wheel on the back of a steamboat as it's pushing water along. Whenever they first turn on this voltage source up here, all of a sudden electricity is going, it's flowing, it's coming through here, and when that beam of light shoots out of there, you should know at this point, light is not considered matter. So light is not matter. Why is that? Hopefully you answered because light does not have mass, and matter has to have mass. So that cannot be just light that's in there, because when this electricity flows through there and all of a sudden this cathode ray, meaning what looks like to be a light there, shoots from one side to the other, that paddle wheel actually starts to move down the tube. The only way it can shoot down the tube is something with mass has to be hitting it so it can roll down this particular way. So there's the other conclusion is, yes, whatever is in that ray has a negative charge, but it must also have mass associated with it. So we're going to get into, so far, J.J. Thomson is going to be our second model that we're looking at. So the two models that we have, we've got Dalton's model, which Dalton said, you know what, everything's composed of atoms. There we have that. And for the atoms, he said they couldn't get any smaller than that. So we're just drawing a circle for that. And then Thomson comes along. He did some experiments too with Millikan. We're going to show Millikan's oil drop experiment here in just a second. But Thomson's going to be given credit with what we call the plum pudding model. If you've ever had rice pudding with raisins in it, very similar. But he said, yes, okay, there is an atom, but I think along the surface of this atom, there are going to be these negatively charged particles that we now call electrons on the surface of this atom. So he's going to be given credit with the plum pudding model. That's the second of 5 models we will talk about over the next couple of chapters. And here we go with Millikan's oil drop experiment. It tells you that Robert Millikan, this is going to be about 10 years or so after Thomson, he determined the actual charge of the electron. So we knew electrons were negatively charged, but he was able to actually put a value to the electron, Please take some notes on his experiment. Get that drawn into your notes.
In Millikan's oil drop experiment, he squirted negatively charged microscopic droplets of oil into a chamber and observed them with a microscope. Voltage applied to metallic plates within the chamber allowed him to create an electric field, which had an effect on the droplets. By adjusting the electric field's strength and direction so that it pushed the droplets against gravity, he could suspend the droplets. By knowing a droplet's mass and the strength of the electric field needed to suspend it, he calculated its charge. Testing several droplets in this way, he found each droplet's charge to be a whole number multiple of 1.602 times 10 to the negative 19 coulombs. This is the charge of an electron.
So, a couple pointers. Again, it says he was able to determine the charge of the electron. The oil droplets were going through these charged plates. You can see the battery that's up hooked to it, charged the plates, and he fine-tuned it and was able to adjust the electric field strength on those plates, and then from that he could actually calculate the charge of an electron. He could calculate the charge of the electron, and there's the value. That capital C is coulombs, which is what they were talking about, the charge of an electron. Moving on to Rutherford's gold foil experiment. So this is going to be a couple years after Millikan. In this one, we are going to come up with the discovery of the nucleus and some information about it. We're going to run through the video first, get a nice drawing of it, and make notes as you go along.
Ernest Rutherford, with Hans Geiger and Ernest Marsden, discovered the nucleus of the atom using a beam of positively charged alpha particles. They bombarded a sheet of gold foil with a stream of alpha particles. Most of the particles passed straight through the foil. About 1 in 8,000 particles, however, were deflected, sometimes directly back at the source. Rutherford explained these results by hypothesizing that nearly all of the mass of an atom is concentrated in a very small volume called the nucleus. If the nucleus were small, it would be easy to miss. Alpha particles which miss the nucleus are deflected only slightly, if at all. Alpha particles which hit the nucleus are deflected severely.
Okay, so when you're making your drawings, that gold foil experiment at the beginning, and then this latter part as they're honing in on one atom in the nucleus, which is really small within one atom, how all of those alpha particles, that's the black lines you see here, most of them went straight through the atom because they're not hitting the electrons either, which are 2,000ths the size and mass of a proton. So most of them are going straight through, but again, it says 1 in 8,000 actually bounce back towards the source or hit some other part of the filter or the screen that is around it. So again, make sure you have those drawn. Take really good notes. You've got your conclusions and some of the things that they saw with the gold foil experiment over here to the left side of the screen. Be sure to get all of that into your notes. So again, the nucleus, very, very small volume-wise, but very dense. So very massive part of the atom for its very small size. Now we can add on our third model. So again, Dalton, smallest particles, the atom. Thomson said, nope, I've discovered the electron. So we have our plum pudding model with Thomson. Rutherford comes along and adds onto that, wait, we have something in the center of this atom that we will eventually coin the phrase of nucleus with it. And we will talk more about the nucleus, but yes, you still have your electrons, but now we're adding that dense center of the nucleus. So that is our third model, as again the scientists are starting to gain more information. So let's look at the composition of the nucleus. It says, except for the nucleus of the smallest type, which is a hydrogen atom only having just the one proton, all atomic nuclei are made of protons and neutrons. And we've already talked about the protons and the neutrons. Protons do have a positive charge. Their charge is equal in magnitude to the electron, but they're opposite charge. And then atoms are going to be electrically neutral because they have an equal number of protons and electrons. You've got some extra notes to add here. Again, atoms are going to be electrically neutral because the charge of your protons and electrons will cancel each other out. That means, and on top of that, the neutron itself is electrically neutral. So the nuclei of atoms of different elements will be different based on number of protons. And so their positive charges are going to change. I'm looking at my periodic table right now, and I'm finding the atomic number on my periodic table. More than likely, that's going to be the whole number above your element symbol. And I see sodium, for instance, has an atomic number of 11. That means 11 protons. I'm looking at carbon. Carbon has 6 protons. I'm looking at neon. Neon has 10 protons. The number of protons will determine an atom's identity. So the number of protons determine the atom's identity. And again, if you're looking on the periodic table, we call that the atomic number. The atomic number is what determines an atom's identity. Now we're going to look at those forces within the nucleus itself, because if you have two protons that are in the nucleus, and you got some of these nucleuses have over 100 protons packed really tight together, when they are extremely, extremely close to each other, there is actually a very strong attraction between them. I know, protons, all positively charged, and you're thinking, well, when you get two positive charges together, they're supposed to repel each other. But because of the extreme closeness that they have, so close together in the nucleus, it develops a strong attraction. A similar attraction is going to exist between neutrons that are very close together, or even when protons and neutrons are close together. Again, neutrons are electrically neutral, but when you have them so close together, there is an attraction that is created. We call these nuclear forces. Make sure you get the definition there at the bottom. It's that short range, proton to neutron, or neutron to neutron attractive forces that are created. And finishing off our notes here, just talking about the size of atoms, we do look at the radius of an atom. It is the distance from the center of the nucleus to the outer portion of that electron cloud. And because the atomic radius are so small, we express it in a unit of picometers. PM is the abbreviation for picometer.